Hello, this is Miss Chambers, and I am going to introduce the squeeze theorem. The squeeze theorem, as stated here, is if h of x is less than or equal to f of x, which is less than or equal to g of x for all x in an open interval containing c, except possibly at c itself, and if the limit as x approaches c of h of x equals L equals limit of x of Alright, so already I'm bogged down in the language of this theorem, and I'm really not sure what is going on. So I'm going to go back to the beginning and try to figure out what some of this means and see if it helps me understand the entire theorem. So first, I will start with this first part here. If h of x is less than or equal to f of x, which is less than or equal to g of x. Just remember that anytime you see function notation, it's basically just saying y values. So all this is saying is the y values of this function is always less than or equal to the y values of this one, and both of these are always less than or equal to this one. So let's look at it graphically. It'll make more sense. So if I have some function, h of x, that's all the y values of that function are going to be less than the other two. So in other words, on a graph, h of x is going to be below the other two. So let's make h of x like this. And then it goes on to say that f of x is greater than h of x, but less than g of x. So it's going to be above h of x, but below g of x. There's f of x. And then g of x is going to be bigger than both of them. So in the context of the graph, that means it's going to be above both of them. All the y values. So that's what this language means. H of x is less than or equal to f of x, which is less than or equal to g of x. All that's saying is on the graph they're stacked. Squeeze theorem is also known as the sandwich theorem because if you look at this, it resembles a sandwich. Middle function sandwich between the top and bottom. So for all x in an open interval, so that means we have arrows, it's continuing infinitely, containing c. So c is just some value, some x value. And then down here it says the limit as x approaches c of h of x equals L. Well, we've seen that before. Which is equal to the limit as x approaches c of g of x. So what this is the limit for h of x and g of x is the same at the c value. So thinking in that way, really what that's saying is that both these functions approach the same y value at this x value. So I need to redraw my graph to make the graph resemble what that's saying. So erase all this, start over. And this time I will make h of x, and let's label it h of x, and g of x, I will make them touch, or almost. Those should be touching. Ignore the fact that they are not touching because they are supposed to be touching. So they share this point. And then f of x is somewhere in between, so it's, well, let's make it a different color. About red. So that would be f of x. Okay? So now I've got h of x is less than or equal to f of x, and they're both less than or equal to g of x, because remember those are y values. And now the limit as h of x approaches c, so we need to label this x value as c, it's going to equal the limit as g of x approaches c. Let's make that c better. Okay? So they're touching at x equals c. That's all that means. So if that's the case, then the limit of f of x as x approaches c is going to be equal to that number as well. So all this is saying is if I have some function f of x and it can be squeezed in between two other functions that share a limit, then f of x is going to share that same limit. In AP Calculus, really, you don't have to completely understand the theorem in order to use it, but it's important that you understand where it came from.